Today we have to continue with this initiative from the MEMS Sensors cluster, which is part of Sensor Council. Today we have the pleasure to introduce another chapter from Region 10 in India. The chapter, the organized activity today is the IEEE Bardhaman Sensor Council Student Branch Chapter, which is located in Hyderabad. And now we have Dr. Sangeeta, who will give us an introduction of the chapter, and we will introduce the speaker afterwards. So thank you, Sangeeta, so much for accepting our invitation to prepare this presentation and this technical talk. So please, the floor is yours. Thank you so much.
Thank you, Geronimo. Thank you. First of all, I would like to thank IEEE Census Council for giving us the opportunity to Vardhaman College of Engineering Census Council to host this webinar. So let me give you a brief introduction about IEEE Vardhaman Census Council Student Branch Chapter. This is under IEEE Hyderabad section in India. So I have just given a brief website here. This is the website which can lead to IEEE Vardhaman student branch page. And in that we have all the societies. IEEE Vardhaman student branch consists of 25 active student chapters. One of them is Census Council, and details of all the chapters and the activities, the EXECOM members, everything is updated into the website. So our Census Council chapter is affiliated under IEEE Hyderabad section. Our mission of chapter is it promotes engagement of students and professionals in census technology and related applications. And how do we do this? We try to have a collaborative collaboration between the professionals, the researchers, and the students, so that they can come up with new innovative ideas into the census domain. The IEEE Vardhaman chapter was formed in July 2021 during the COVID times. This is a team that is being there. I belong to Vardhaman College of Engineering, and I look after all the professional societies there. Advisor is Dr. JVR Ravindra sir. Chair is Chair, Vice Chair, Secretary, Treasurer, and Webmaster. These 5 are the student members of our college. So M. Hita Reddy is a chair. Vice Chair is N. Sai Saket. I guess they all are present now. Secretary is Sai Chandu. Treasurer is Meghna, and Webmaster is Parthiv Reddy. These are the 5 active student members who have been added to the EXECOM of Census Council under Vardhaman College of Engineering. And one good thing that our college is, it encourages IEEE members. So in our college, we have around 220 members, combinedly faculty and students, who are members of Census Council. This is the poster that you can flyer, where you can see the student members. In between, we have a faculty advisors, and either side we have a students. The names that I have mentioned, the pictures are shown here. And IEEE Census Council Vardhaman chapter is quite active. We do organize technical talks. We have organized DL programs. We have organized a nationwide Vega workshop in association with India Council, where students were trained on applications of census. Then we also have organized professional development programs involving industrial IoTs. And last year, Census Council have started a IEEE MEMS training program, and the students of Vardhaman College have actively participated in that. And also one team is going for the fabrication also. Then recently, our team has organized a Sensoverse competition. It was a diverse competition where students were given some problem statements, and they were asked to solve it. And in addition, Vardhaman is quite close to Hyderabad section Census Council chapter, where we have collaborated under a number of events for seasonal school and women in census event also. These are few glimpses of the events that we have organized. We had Sanket Goyal sir, who has visited our college. We have Paula, who is chair of Women in Sensor. She also visited our college and they delivered and interacted with our students. Deepak Mathur sir, Celia Shenas madam, they have contributed and they have shared their research with our students and faculties. So that's all, because it was a short introduction about our college. And thank you for giving us the opportunity. Shall we continue with the introduction of the speaker, Geronimo?
Yes, please.
Yeah. I would invite Hita, who is the student chair of Vardhaman College of Engineering Census Council, to introduce our speaker for today, Preeta ma'am. Hita?
Um, Thank you. It gives me immense pleasure to introduce our distinguished speaker, Dr. Preeta Nair, obtained her MS in Physics from Cochin University of Science and Technology and PhD in area of fiber optics from Indian Institute of Technology, Madras. She is university rank holder of her MS degree in the recipient of Lasker Award of Best Thesis in Physics in 1997 from IIT Madras. Dr. Nair has over 26 years of teaching experience. Her research work focuses on areas of optical fiber networks, silicon photonics for optical communication, photonic sensors, and acoustic metamaterials. She has successfully completed various projects sponsored by Defense, AICTE, NRB, BRNS, and industry. During her academic tenure, she has supervised 8 PhDs and is presently guiding 4 more PhD students. Dr. Naya has guided over 14 UG final year BTech projects and 11 PG projects in related areas. She has initiated interdepartmental research labs, the National MEMS Design Center, and Optical Research and Network Labs, apart from EO Thin Film and Sonic Metamaterial Labs. She has over 90 publications to her credit and is a member of IEEE Photonics Society, Optica, life member and governing council of ISSS, Institute of Smart Structures and Systems, and life member of AIST. She has been an active proponent of all e-learning and virtual learning endeavors. At present, apart from her role as professor of physics, she also serves as academic council and board of studies member and controller of exams at Shiv Nada University, Chennai. As part of IEEE Vardhaman Census Council student branch, we are truly honored to have such an accomplished academia and research among us today. Someone who embodies the spirit of scientific innovation and mentorship that IEEE stands for. On the behalf of IEEE Vardhaman Census Council student branch, I take immense pleasure in welcoming Dr. Nair to share her valuable insights and inspiring words with us. Ma'am, please.
Yeah, thank you, Hita, for such a beautiful introduction. I don't know whether I really deserve it, but anyway, thank you for that. I hope you can all see my screen. Am I audible?
Yes, ma'am.
Yeah. So I was told that many of you are newcomers into the MEMS field. So I have added a few slides which are probably introductory. When I gave the title, that was not what I had in mind, but I've actually changed accordingly. So we'll make a beginning now. So what is it that we are talking about? Anything which you are working in, you should have some idea of what is the market available for you, because the product has to sell, right? So if I look at all the predictions which many different groups have given on the market growth for MEMS as a whole, it's supposed to increase from 17.5 billions of US dollars to 30.8 by 2032. And if you really see what is actually driving this market, it's mainly point of care diagnostics, wearable, flexible, high tech, applications in food and beverage, and environmental requirements for sensors, requirements for industrial monitoring, and also for the communication part. So if you really look at the MEMS as a whole, micro electromechanical systems, as the main name suggests, is actually meant for sensing something using structures which are freestanding, which means it can move. something like a membrane which is moving, which can sense the pressure, or maybe it's a piezoelectric membrane so that you can drive a acoustic signal in. It can also be used for actuations. But when you come to think of applications, you will actually, what are you going to do? You're going to collect the data in, make some sense of the information which is available for you. So that is where the intelligence coefficient comes in. And if need be, if it is possible, we will try to take a proactive action based on that. So initially, in the initial periods of MEMS, we were having standalone devices which were actually doing the sensing and reporting what's happening. And we used to uh, take the readouts and do our own version of interpretation, and we used to do what we really wanted to do with it. But now the technology is actually going in such a way that we are actually thinking of not just one dedicated application, but we are looking at multiple data coming in from different devices, because you want to know how the environment is affecting you. You want to know how our systems are working internally, and then you want to communicate you are okay, not okay. So if you really look at it, it's actually a combination of many things which we are now looking at. So what are we actually looking at now? We are actually looking at trying to extract multiple parameters. So you are now not talking about just one sensor, but you are talking about collection of sensors which will give you different inputs. And you are talking about building a contextual awareness, saying that, okay, what is happening around you and how should I react with that? So you are also looking at how you can leverage this understanding and essentially look at how you can come out of it. Can we take some proactive action based on what you're having? So it's what we are moving towards is a AI-powered multi-parameter, multi-sensor modality. And can these sensors, because they are all when they age, and then on there might be issues when you are having temperatures which are influencing the sensors parameters, etc. Can we do a self-calibrating? So those are the directions in which we are actually progressing. So for the benefit of those who are just into MEMS, because I think it will sink in better if I can give a bit of a introduction to the MEMS as such before I come back and see how we are actually doing all this now, so that you know what is currently happening in the MEMS field. I'll just look at some very introductory materials. I hope yeah, those who know MEMS already will uh, pardon me, but it's for the benefit of those people who are actually listening to what MEMS is for the first time. So what micro electromechanical system is basically what we are looking at is a system which incorporates some freestanding mechanical structures which can be either made to move, or it moves by itself because of some physical parameter you are sensing, and then you are transducing that information, okay, into either an electrical signal or an optical signal or a magnetic signal which you are tracking, and then you are building a system around it. So it's not just a sensor alone, but it's a sensor along with its circuits, along with its communication channels, etc. And typically it is done on a silicon platform, and which means that it is it has to follow through a standard CMOS batch processing techniques, just like your VLSI circuits. So it's a combined system. And by moving structures, I mean it could be mirrors which can tilt, it could be gears which can move. So these have to be realized on a planar platform. So that is what we actually call as MEMS. And essentially, finally, it will be like a system on a chip. So one of the best examples you can think of is probably your own mobile, which is having a collection of sensors, just like I was telling you, multi-parameter sensing. You have your accelerometers, you have your gyroscopes, you have accelerometers to help you shut the system down while you are where it's being dropped. You have gyroscope to turn your screen. You have electronic compasses on board. You have pressure sensors on board. And this diagram is a pretty old diagram if you really look at it. You have acoustic, you have your microphones, you have your antennas for receiving, right? All of them may or may not incorporate moving structures, but many of them do, especially the accelerometers, gyros, etc. Right? And you have your RF antenna on board, you have Bluetooth for connectivity, and now it's not a rigid structure, you are having a very flexible platform. So essentially, you may not have all the implementations may not have, especially in case of biological applications, it may not be on a standard silicon platform. It could be on flexible structures, which we'll just look at as we go down. Okay. So based on the domain of application, you can call it that, okay, it's an optical application. So it's a micro opto electromechanical system. If it's in the RF area, you might call it RF MEMS, you might call it bio MEMS, but now you are slowly losing these distinctions. These were, remember, I am telling you about how we all started with in the MEMS field. Now we are talking about a plethora of sensors doing everything collectively, as I told you. And just to give you a rough idea for the newcomers on how we actually make moving structures, you let's look at electrostatic actuation. I'm just picking up a few of them for illustration purpose. So it's very basic structure. So you have a dielectric and you apply a field. You have charges building around, the material gets polarized, and you have surface charges building. And if this is not a rigid structure like that, but if you can split it out and one of them is fixed and one plate is movable and you have the dielectric in between, then you can have the gap changing, which essentially means the electrostatic force is changing, right? So if you leave it free to move, the positive and negative charges will start, the electrostatic forces will start to bring these two plates together, right? So, and the force is actually inversely dependent on the square of the distance. So these were the initial MEMS capacitive sensors which were made. So the electrostatic force actually makes them come closer together. So if you, and as they come closer, the force keeps increasing. So finally they'll snap down together. So you can make contact switches if you want to use that purpose. But if you want to release it, then you have to actually remove all the charges and then you can start over again, right? So how do you increase the force? But I don't want it to collapse. I don't want it to be a contact switch. Then I have to control it. So we have to increase the capacitance. We have gone in for uh, interdigitated structures. So you have essentially, because you are having an increase in the uh, surface area because of these comb structures, your surface charges increase, the force increases. So it's basically the area which is changing, and this is on the spring. So if you apply a voltage, according to that, it's actually going to move closer and closer. So that is one way of realizing a larger force, which is independent of the gap in between these electrodes, but actually the surface area of interaction is increasing, right? So you have a tunable capacitance coming that way. So you have different applications based on, maybe you want to make a oscillator, maybe you want to make a sensor which is actually it's left free and it's moving because something is making it move, and now you have a change in capacitance you can track, which is actually now working. In that case, you are actually working like a sensor. If you are actually wanting to move closer and therefore realize some effects, then you will be applying the voltage and getting these free moving structures to move according to what you want, right? And the way you can read out, there are a number of ways. You can look at ST microsystems, for instance. They have it moving at its resonant frequency. So any small change in the system, the resonant frequency will shift. So it's a very, very sensitive tracking of capacitance change through actually tracking resonant frequency, but not actually tracking the capacitance which is there. So there are different modalities in checking, but since this is just a overall introduction, I'm not spending too much time on all these. I'll just show you a few examples of what we have done, since I am mostly in the photonics field. What I have here on the screen, if you look at the top, there are 3 plates which are essentially 1 micron each. So a Fabry-Perot filter is something you have 2 mirrors separated by a central cavity, and the wavelengths which are passed through this filter is basically based on the thickness of the central cavity. So if you can tune the central cavity, you can select different wavelengths out. Okay, so that was the main intention of making this. But I wanted to select a wavelength depending on my setting, which means I have to have control over the central cavity there. So I send in multiple wavelengths to the waveguide, and what comes out into the receiving waveguide is because we had done it for communication purpose, we wanted a traditional 1530 always coming through as a sort of a supervisory channel, and we wanted to add on some channels in the C band, which was where the digital TVs were being added and dropped, right? So if you look at this structure, you can see the combs on the top. This area is where the combs are. So these three plates together form a Bragg mirror, and these three plates together form the second Bragg mirror, and this is the cavity in the center. So it's freely suspended, and when you apply a voltage to these combs can move in, which means the plates are going to come closer and closer, and that is how this tuning is coming. So if I was at 3 volts, I would have got a wavelength close to 1570, and as I keep going higher, I'm able to tune the wavelength, which is added onto the receive waveguide, right? So this is actually done through electrostatic actuation. Now I can think of different applications for the same device. We did it for communication aspect, but then I can easily use it as a tunable filter or as a spectrum analyzer, because it's actually dropping out specific wavelengths based on the voltage I'm applying. So I can have the same thing here, right? But instead of having a waveguide, I put a slot in so that I can introduce a single mode fiber and take a single mode fiber out. So this can work like a spectrum analyzer for as I change the voltage, I'll be changing what I'm receiving in the fiber. So it is doing a job of a mini spectrum analyzer. Now, if I can also envisage a structure, there's a structure on top, which you are not seeing, but I can show it to you a bit later. So this is that central structure. So if you really watch this while I play, you can see that I'm just operating it at close to a high of AC frequency so that you can see it moving, right? So as you move, the wavelength which is dropped will change. So that's the main principle behind this. And if I don't make it moving, I can still have other applications because I have a fixed central channel. I can send a microfluid. These are around 5 micron in size. For you to get an idea, your human hair size is roughly 125. So 5 micron means it's less than 1/10 of that, right? So through this fluid, through this channel, if you send in a fluid, I can have a source here, and I'm looking at the spectrum which is transmitted. Now, depending on the refractive index of the fluid which is flowing through the central cavity, again, there's a refractive index change, which means the optical path length changes, and therefore I have an RI sensor. So I have a microfluidic RI sensor, right? So I'm just showing you different applications just based on electrostatic actuation. Okay. Now let's look at another application. This is not exactly in that field, but you can see it's the same device which is there. I can change it into, let's say I have an IR source and I have a chamber which is transparent, and I've introduced it through this T junction. I've created a slot here. I've introduced the chamber here. It's a biofluid which is latching on to antibodies and antigens, and it's giving you some fluorescence or absorption. So I can actually do a study of what is the absorption wavelength of it, because I pass from the source the different wavelengths, and then I look at what are the absorption peaks. And if this whole chamber is fully transparent, I can still have a microscope, and on top I can look at the fluorescence, I can look at the imaging part. So if I have a impedance analyzing some kind of a electrode system at the bottom of this chamber, then I can do an impedance testing also simultaneously while these kind of chambers are important. If you are looking at, say you are tackling some new genetic disorder and you have sort of isolated it, but you don't know exactly how to stop it, you might have to see the actual growth of the disorder. So the cell will be under observation throughout, and you will track it using different means. So your sensing modalities could be different in this particular case. So I'm just using one example to show different areas in which it can be used and how you can make it multimodal. Okay. Now let's look at some other means of actuation, which is electrothermal. So in your electrothermal means, what you are looking at is, sorry, you sent current through a device and you know there's joule heating. So if I don't want to use different materials, I can create a biomorph kind of thing by having current flowing through areas which are different. You know that the resistance is basically rho L by A, where rho is the resistivity and L is the length and area is the area of the device through, I mean, area of the section through which the current is flowing, right? So if I look at the structure, the resistance offered, the thinner arm is going to have lot of current. The same current is flowing through, but the heating I square R loss is higher here. So the thermal expansion will be higher in the thinner arm, and therefore it starts bending. So you are creating a bimorph not by having two different materials, but by making geometrically differences, right? So we call them geometrical bimorphs. You can have many structures like this. If you see there's a small angle here, there's a central beam. And if you send current through the beams, which is shown here, if you send a current through like this, then this beam is expanding, this beam is expanding. But since this is connected at a certain angle, this will push the whole central beam forward. So you can have a electrically actuated motion because of joule heating. So we call it electrothermal actuation. We can always use the metal dielectric biomorphs, which you are all I think familiar with. You can have a material which has a high temperature coefficient of expansion coefficient, and have it over a material which is having a lower expansion coefficient. Okay, so if it gets heated up, the material will expand, the one will expand more than the other, and therefore you are having bimorphs by themselves. So this would require a metal dielectric or two materials which are entirely different in their CTAs, right? So these are the ways you can actually realize electrothermal actuation. So I will just show you in the next slide one such application which we had done. These are all specific products for specific applications. Okay, so this was meant for a satellite payload distribution actually. So the idea here was that if I throw the switch, I should be able to connect it to 4 different outputs. Or if I throw the switch in another way, I should be able to connect to 2 different distribution channels. So 4 users, I give the same data, or 2 users, I give the same data. But the design requirement was that RF isolation should be greater than 30 decibels, and there should not be any heating happening close to where we are intending to capture the RF signal, no interference there, right? So the design principle was that if you can bring 2 waveguides close up to around 1 micron, then there can be a lateral coupling of the RF signal from the one channel to the next channel. So the central beam that you see here is actually going to move. The whole RF part is out here. The RF signal is applied to the top, sort of U-shaped thing. Okay. And the output ports are all there. It's well away from where I'm using the electrothermal actuation. So if I send current through one of these bottom beams, there's a small angle there, it will move forward. But if I send current through the bottom ETA beam, then what will happen is that it will pull it down. So I can have an up and down motion. And using that, we are actually trying to connect between 4 ports or the 2 ports. So if you really watch what is happening in the image which I have shown on top, when the beam moves up, okay, when the beam moves up, so from this port here, from the port, this is the input port, both are inputs, okay, which is this portion. This is an optical image which was taken when it was actuated up. So you can see that this beam is connecting. So the input is connecting, and this is more closer than 1 micron. So it couples into 1, 2, 3, 4 ports simultaneously when it is moving up. But when it is moving down, what happens is that the beam has now moved down. You can see that it's moved down. So the the input is coming from here, but what it is coupling to is one channel here and another channel there, right? So the intention was that we should have a good degree of isolation between that, and these curves below are showing that we are achieving good isolation both for dual as well as the quad distribution sync. So this is an example for electrothermal actuator. Now that you have seen previously how I've used a filter, if I want to show you an example with I'm sorry that the screen is pretty small, I mean the image is small, but essentially you have a mirror in the center and you have a metal bimorph here. So you are having a metal layer above the dielectric, and you're also having a metal layer below the dielectric. So I can make each of these move up or down depending on whether I send current through the top half or where I am sending current through the bottom half. So if that is the case, why we were looking at this design is we wanted to make some photonic crystal structures like this, some pattern like this, and I wanted to create a defect there because where there is it's actually meant for creating maskless interferograms. Okay, so if I can create patterns here and that is etched into the photoresist, then I will be actually translating this into holes in the material. And where there is no structure, I am going to have actually plain silicon sitting as such. So I will have two waveguides which is separated by a low index region, right? So, but this I wanted to do with some 200, 300 nanometer intervals, which is very small, which I cannot do using standard photolithographic techniques. So I have thought that we will use interference lithography and have a group of mirrors, okay, and generating multiple beams, which will create an interference in this pattern. So essentially, this was the idea, have these mirrors there in a hexagonal packing. And all these mirrors, one beauty about hexagonal packing is that it's closely spaced, and all the ones at a particular radius will have more or less the same intensity. The center mirror would be, if it's a Gaussian profile of the laser beam which is incident, the center one will have more power. But by tilting the mirrors on the sides, I can get a 2 or 3 or 4 beam interference as I want to and get structures which I really would like to see. So we work backwards and see how you can actuate. So this is an electrothermal actuator based on bimorphs, but I need to have multiple layers there. This is just based on silicon alone, right? And that's a geometrical bimorph basically. So these are two applications where I'm showing to illustrate electrothermal actuation. Okay, so let me go back quickly. Yeah, I'm not on pointer mode. Right. So another application this can be is for making different beam shapes. I can make a convergent beam shape. I can make a divergent beam shape so that I can look at, open line of sight communication for wireless also. Now, if I look at the same thing, this is for gas sensing applications. I have a gas chamber through which I am having different gases flowing. If I look at an area between 4 to 6 microns, typically, these absorption peaks of carbon dioxide, nitrous oxide, carbon monoxide, etc., will always have some crosstalk with hydroxyl ion absorption peaks also. So you have to find an area where the cross sensitivity due to water absorption is slightly less so that you can be more specific. And we picked this area mainly because of that, this range of 4 to 7 microns. So you need to have a IR source there, and you need to send each of these beams in and see how much is the absorption. Carbon dioxide has a specific absorption wavelength, and nitrous oxide has another, and CO has another. So this guy is actually like this is showing an electrostatic actuator, but I can actually also do electrothermal. This is one design which is there. I think this was done recently, probably. The thing is that I can get the tuning whenever the spacing between these two are integral multiples of lambda by 2. So if I have this initial separation between these two Bragg mirrors, okay, it's please, I'm using the same example so that I don't have to go into different concepts. So the same Fabry-Perot filter example, if I keep the spacing at 5 microns, and if I apply voltage at the top, okay, to the top layers, then what you will find is that this beam in the center is actually moving away. So from 5 micron, I can easily go to 10 microns. And if I am applying voltage in the lower half, I will find that from the initial 5 microns, this guy is the one on the left side is going to move closer to the one on the right, which means the gap is reducing. So I can actually go up by 5 microns, I can go down by 5 microns. I will get different sensitivity while I'm actually trying to track what is the delta lambda change for the applied voltage. And what is the applied voltage which I require? This is in millivolts. It does draw a current because it's electrothermal. So the design here is having a push-pull configuration so that while this moves, this also pulls so that you get an effectively larger motion. So here the motion is around 5 microns, whereas in electrostatic actuation, the motion is only around 300 to 400 nanometers. And for that, you require around 3 volts or 4 volts. Now, here the voltage requirement is few millivolts, but the current is there. So you do have power consumption. So that's the drawback of using electrothermal actuations. So this is another means of actuation. You can have phase change based actuation, which is the next one which I have as an example. I'm not showing a magnetic actuation. Magnetic actuation would require you to have a permanent ferromagnetic layer to give a permanent magnet, and then you can have a coiled system there. So you have to implement, remember, you have to implement all this in planar structures, which is pretty complex. But you can have a magnetic magnet induced motion. But those who are, when you get deeper into MEMS design, you know the magnetic forces when you scale down the sizes are actually not that good. So that's why initial periods we've not been concentrating on magnetic sensors, magnetic actuation more. We've been mostly doing electrostatic and electrothermal. But now that we are learning to make a ferromagnet layer, put it down, etc., and then do it sequentially, even though it's a bit complicated, you can still, one big advantage of magnetic sensors that you don't need to have to keep on having power losses, because once the magnet is on, it works mostly, right? So you only need the electromagnet part of it to work. So the power requirement will be extremely low if you can go for magnetic actuation. So I'm not touching that just because it's, I don't think I'll be able to cover everything. So this is phase change materials. Those of you who may have studied in your initial years in engineering, these are shape memory alloys. So it's basically titanium nickel combinations which are used. And when they actually undergo a phase change and therefore a structural change also, the dimensions change when it is heated. So this is showing how a small current passing through the wrapper holds it flat, but when you remove the current, it actually closes to form a kind of a wrapper. That's on the extreme right. Okay, so you can hold things which are, you need tools to hold 100 micron wires, you need tools to hold nano-sized structures. So you need essentially devices which can do that, which can move and hold and release when you want, right? So the bottom shows you a mirror again, but it's actuated through a beam which is actually made of shape memory alloy. So when the current passes through it, it heats up, it contracts, and therefore it lifts the plate up. So it is lifted up in each corner, and therefore you can get a multi-axis motion of your silicon mirror. Of course, if it has to function as a mirror, you can have a good metal layer on top of silicon also, right? But silicon itself might give 60-40 kind of reflectance. But if you really want 100%, you would like to have a metal layer on top of the silicon. Apart from, this is only showing the hexagonal shape of this mirror, right? So these are different ways you can actually initiate actuation. And since I am an optics person, I will mention also the optomechanical motions, where you may have studied in school when you are studying that the radiation induces a pressure, and you talk about radiation pressure. But in macroscopic systems, you don't actually see your tables moving because of the sunlight is there, right? But if your structure sizes are very, very less, then the electromagnetic force of the EM wave can actually give enough radiation pressure to move nano-sized things, right? So this is an example on the right-hand side. It's a biomedical optical trapping application. So you send in enough power through the waveguide. From the waveguide, it couples into a resonator. So the electromagnetic field inside the resonator is pretty high, and the field can trap a nano-sized particle. So you can trap it for the time the signal, electromagnetic signal, is present. So if I want to release this blue-shaped nanoparticle, all I need to do is switch off the power in the bus waveguide, and automatically this particle will get released. So it's a non-contact, way to observe a nanoparticle. Another way to do it is, if you don't want to make this 1D crystal, because this is again going to be nano-sized, and to make it is tedious if you don't have good fab facility access, then you can go in for a micro ring kind of a structure. So from the waveguide, couple into a micro ring. Now this is a resonator, whatever wavelength which is going through it. If the total path length through this is integral multiples of lambda, then it will get sustained and it becomes a resonator. Now, if I can cut the resonator and make a small nano-sized gap in between, okay, then the power will still go through, most of the power will still go through, but the field is actually now out in the external surrounding also, which means if a nanoparticle is passing through, it will get trapped by this electric field, right? So this is another way you can actually use optomechanical force to actually do some observations, okay? So this is a rough idea on how we do actuations. So when we come back to what we were trying to do, so these were all applications where I showed you mainly one or two devices typically being actuated in different ways for different applications, right? Based on the requirement. So what we are now into is having a plethora of sensors simultaneously giving you an understanding of the inner world in which you are and also the outer world, and then make some decision, right? So one of the best examples, if you ask me, is probably flexible health tech things. Let's look at let's say somebody has some problem in the heart, you take an ECG, but ECG is capturing what's happening inside at that point of time only. Maybe the heart is skipping a beat in between, the pace is not correct, the pulse rate is increasing and fluctuating. What leads to that would require continuous monitoring over a period of time to actually, which means you have to keep taking ECG over a long period of time. Which means, so if you have to do that, you have to have it on your body, maybe for 12 hours, 14 hours, 16 hours. And then since you are putting it on the body, you measure the heart rate, you measure the body temperature, you look at how fast it's beating, you look at the blood pressure. So you have a multitude of sensors inside. You have these, this is slightly big. It's not fully flexible in that sense that it's not very lightweight, but it can be stuck onto your chest, right? And can be on. And how do you get the signal out of it? You have a Bluetooth which will connect to your mobile. So you have the communication system there. That's where the GPS and the Wi-Fi comes in. Okay, so that's also on board. And from there, you don't do the processing on the mobile. From the mobile, you dump it onto the cloud where it's processed, analyzed using AI, and then the results are either taken up and given to the medical advisor or returned to the user so that they will have it in a report form. So it's like a continuous monitoring, and you can find all the details in the particular paper which I quoted here. It's just a figure from there. So the substrate used here is basically a flexible material which has electrical conductor, that is copper on top and bottom, and a polyimide rail in between, and these are sandwiched together. So it's a laminated structure. It's similar to the base of your flexible mobiles. Okay, printed circuit board of your flexible mobiles. Apple Watch is again an example which you are all well aware of, right? Where you are monitoring so many things and reporting back to you, right? It also has multitude of sensors which are on watch for you, looking at what the outside temperature is, what you are doing, whether you walked enough or not walked enough. So a lot of AI coming into the picture is what I'm trying to tell you. Now, can we all use in this particular example? We are not taking any proactive action, but if you are looking at insulin injection, you have microneedle patches on your skin and it monitors your insulin level. If it's less, then it actually releases through the microneedle some dosage based on how much sugar you are having, right? So in that case, it's actually taking a proactive action to prevent you having either very high sugar or very low sugar, right? So that is what I mean by proactive intelligence, which means you collect the intelligence and you also act upon it then and there. So which the device should also be able to do a proactive uh, correction for whatever is happening. So that's where we are heading, right? So most of it, if you see, many of it is mimicking what's happening in the biological world. You must have heard, I think there was a lot of things on Opportunity Mars in the YouTube also recently. So this rover was one of the first rovers sent in 2003 by NASA, expected to last around 90 days, but it lasted 15 years, right? It went around, shot everything, but after 2018, it was exposed to a very, very big dust storm, and the last message was the batteries are low and there's no light. Remember, this was launched in 2003, and still it was rugged enough to work all these years. But could we have prevented it by being proactive? Yes, if you could have monitored the particulate impurities which are coming in, seen that it's going to impact the camera, impact the solar panels, light is not sufficient. Can I still take an image when the light is less and have all the colors which are generally visible to us in the visible? Can we do that? Some kind of a wavelength based distinction even in the night. Could we have done that? Yes, look at forget me nots. If you apply pressure, this guy just collapses, and looking at the amount of pressure you are applying, it just folds in, right? So you could actually think of devices which will actually go into a shutdown mode if the dust particle sizes are more than a certain value. Of course, people are now doing it. So this is just to tell you something about how proactive sensing and actuation. So you need actuation there basically to make the corrections, right? Shut down things, go and hide behind somewhere, protect yourself, right? So another example I can take from nature is the gecko eyes, right? So gecko is a kind of lizard. The big benefit its eye has is that it has three concentric zones which are having different refractive powers. And it has we know that our eyes have rods and cones. Rods is for vision in the daytime and cones is more for night vision. So these guys have slightly oversized cones. And if you really look at the aperture, when the light is very high, it's just, small pinpoints. I don't know how clear it is in the picture here, but these are just 4 dots which are opening into the different zones of the 3 different zones which are there, which means it's creating images at multiple depths because the refracting powers are different, right? So it has a multifocal system. And when the light is not sufficient, it actually opens up more. So this is actually telling you the pupil's area as the light intensity increases. When it's increasing, it shuts down. When it is less, it actually opens up and becomes bigger. And even in night, it's able to have color vision. It's able to correct for blurring visions because you have internally 3 different depths which are being focused. So it has some idea of, okay, it's blurred now, it is correct now, and accordingly it can adjust the light intensity falling into the different zones and get it focused more. So minimum it has at least 2 different depths which it can see at the same time. Now, can we mimic this into our camera? Then you have a really good system, right? Which can take proactive action based on what you are encountering, right? So let's look at one example, probably in the electromotive sector. I think I've taken up a car because you have self-driving cars. Look at the plethora of devices, mostly inertial navigation systems, airbag for accelerators for deploying, emergency calls. You have tire pressure monitors, which is not actually shown in this picture. So this was from ST. So it's basically using all ST sensors. Their accelerometers are 6-axis accelerometers. So you can look at roll and pitch, gyros, all of them are there. You can communicate, you can look at what is the health inside, whether the driver is sleeping, because the driver is also being monitored on the camera. You have sensors on the seat. You can actually look at noise cancellation from outside. Okay, you don't want the outside noise to come in. You can do some cancellation based on the sensors you put there. So you have so many sensors put together, and then you are having AI on top of it to actually make sense of what all these sensors are saying. So let's look at, come back to the slide which I come to. I hope I have given you a introduction to different actuation mechanisms in MEMS and how we actually club many things together now and try to make sense using AI. But one thing which we need to be very, very careful about with using AI is that it needs training, it needs computing power. So you don't, if you want it to be cheap for the user, you do not have it on board right at the point where you have to use edge computing, or you have to pre-train train the machine model and then use it, so that you use very little computing power on your system essentially, which is closer to you, right? So, and we are trying to shrink the sizes to nano dimensions without impacting the detection sensitivity. So these are the directions in which we are actually proceeding. Okay. So if you look at the role of AI, the requirement, let's say from the point of view of an industry, would be that the production line should be up and running. It should have speed and accuracy. You have to find the fault out before the production stops and make a corrective action. If you are looking at environmental things, you need to know how the work environments and the tasks are getting at this thing. If you are looking at biological applications, you have to look at how small physiological changes are going to affect your system, right? But any AI training has common issues, right? You have any ML training, will give you accurate output based on the size of the data and the quality of data you had used for training. And whatever you do and say, over a period of time, these might change and you might require a retraining. So the validity period of the training data is important. You have to keep monitoring in the production line. They have to keep saying that, okay, whatever the outputs the model is giving is now not really matching what is existing. Therefore, what is the correction needed? Do you really need to go in for a complete retraining based on the new inputs which are coming in? You should always keep your power and computational requirements low. So if you really look at what are the areas in which AI is coming in the sensor design, it comes in two ways. Let's say I want a filter made and I have certain parameters, and I have certain outputs, so I will train the machine learning algorithm. If I have the structure like this, and these are the voltages applied, then this is the spectrum I will get. Then I can ask the AI, once it is trained, the machine learning algorithm once it's trained, give me a design to get me the spectral output I want. So it's an inverse design, right? So that is where one area in which AI is playing a major role. The other is in, okay, while we are designing, there are fab related issues. So however much you design, there will always be a small mismatch because of fab artifacts if you've not modeled it incorrectly. So you can use some AI-based trained optimization during a design cycle. You can look at how the circuit is functioning, and can you reduce the thermal component? Can you improve the signal to noise ratio? So you can have AI working on the signal processing side. You can look at the battery, whether how long the battery is going to last, right? So you can have trained models there. So the one area is in the sensor design in different forms. The other is in sensor calibrations, because once a sensor is made and you have calibration data available, you can train the MI algorithm based on that, and therefore it can use that for actually giving you a scenario which is correct based on all the sensor inputs which you are giving. Because now we are having multiple, remember we are talking about multiple sensors being there, and each one has its own sensitivity and its own calibration, and you need somebody else to sit and see that, okay, what is the total output? Which sensor should I bang on when the temperature is high? This guy will give me more errors, so I should take the output from the other guy which is more stable to temperature fluctuations, right? So these kind of issues will come in, and that can be done through pre-training. And since it is already trained on the previous calibrations, it can also do some auto calibration runs, which is what we are moving into. to offset supply noise, offset the temperature-induced effects, offset the aging phenomenon which could be there in your sensors, etc. So this is one area where you will find a lot of papers on the role of AI for giving proactive intelligence. The other area is on other standard things like object identification and classification. You can look at, if you are having flexible electronic systems there, you can look at how human behavior is. If the guy slept properly in the night, you can have sensors on the sheet. Now they are coming up with sensors on the baby's blanket to see how the baby's health is, okay, without the baby being aware of it. So every feature of the child is tracked. You can have in the industrial areas, you can have in the production line, you should have a mechanical fault detection, right? Can you identify the tool wear before that starts affecting the production line? Can you identify the gas and radiation leakages and do some corrective action for that? And the other area is, can you do an inverse control for imaging tools? I will give a small example there. So that I introduce you to optogenetics, and I should thank NCYU in Taiwan for that. Okay, so optogenetics is basically a light-based control of neurons. So if you can excite the neurons, and the neurons have a biofluorescence when they are the calcium channels are actually working, then using the biofluorescence, you can observing the biofluorescence, you can actually track the neural activity, the path through which the axons are communicating, synapses, and actually the full neural circuits. So we take some species which has closest, match to the human brain, then you can actually map what's happening there. So fruit fly, normal fruit fly, Drosophila is its name. Its brain, most of the genetic defaults which are happening there, neurodegeneration and metabolic diseases, are more or less 60% common with our human disease gene. So if you can track something there, you have a neural imprint of what's happening inside. For that, you need to actually track what's happening, all the neuronal activities. So to really study that, what they actually do is use a TI Sapphire. Actually, you should excite with UV and observe the fluorescence when the you have to instigate the neural activity through 2-photon absorption, because the TI Sapphire wavelength uses 920. 2 photons of 920 will give you close to UV. The biofluorescence, which you will observe, so the Drosophila is actually frozen. It's like putting that guy under anesthesia. A small incision is made on the brain, and then the light is sent through. So this portion in the figure is basically a polarization half-wave plate and a controller and a shutter. So together it can control the attenuation. You have a MEMS device here. It's a tunable acoustic gradient lens, which means it can adjust the focal length. That is, what is the depth at which finally you are going to scan the brain. So that can be controlled through this. I think you are all using smart mobiles now. You have a liquid lens there, right? So this is something like equivalent to a liquid lens. So you have you have a liquid. It's slightly different from the way it's implemented in mobiles. In this particular system, you have a liquid inside, and then you are applying piezoelectric material all concentrically, so that in the center, when the acoustic beams are switched on, you have a high density. It's a constructive interference, and therefore the refractive index of the material changes, and depending on how much it changes, your focal length will change. So this is actually a MEMS device. And then you have two mirrors, which are again MEMS devices. So this gives you X and Y motion of your focus spot on the on the biological sample, and tag lens makes the focal point go deeper inside. So the neural activity might not be the sample here had around 100 micron total thickness, but if you really look at it, the neural activity might be occurring maybe not at exactly at 100, it might be occurring at some other value in between, right? So you have to change the depth of focus and find out where the neurons are, and you have to excite. So there are two things here where the AI comes in. So this was a good example for both MEMS based tooling as well as uh, a control system which is based on AI. Okay, so what you see here is the green light which is picked up by the imaging portion, PMT, and you are using that as a feedback and you are synchronizing. So it's called a dual resonance scanning because XY scan is synchronized, the depth scan is synchronized. Okay. And the signal to know, because it's fluorescence, you might not capture everything in one go. So you may have to integrate over multiple images to improve the signal to noise ratio. Now the question is, after you do initial rounds and identify where these neurons are. So on the screen on the right, what you are seeing was that as the depth increases, at some point you can see the emissions, bioemissions is dominant. Then as the height goes up, again it goes down. So the tag lens is scanning all through the sections. So it's a volumetric scan. And at each of these levels, each of these sections, you integrate over many till you get sufficient signal to noise ratio, right? So, but initially you don't know where the neurons are, means you will just have the light, UV light falling all over the place. And once the neural activity is mapped in maybe in the first image or so, you will actually use AI to excite only those regions where the activity is done. So you focus all the energy into those patterns, right? So that is where the AI comes in. So the patterns, the required patterns are identified, where are the neurons and how you should excite it for each depth. And that is given as a feedback. And you are having a spatial light modulator, which is actually liquid crystals, an array of liquid crystals. So you will send the light through and the intensity of the light can also be controlled. The phase of light can be controlled. So you are doing that to generate an interference pattern, which matches the profile of how you should excite the neurons. Okay. So actually we went there because we wanted to generate, remember I had showed you something where I had different patterns which I wanted to generate on my maskless interferometer. We thought we'll go and make a mask or a mold which has the pattern which I wanted. So if you give the pattern to the AI, it will actually control the whole array of SLMs to generate the pattern for me. And that pattern can be etched and that can be used as a mold. So this is the application for which they are using there. It's optogenetics. Okay. So if you come back to it, so this is where I was telling you that it need not be that you are looking at a specific application. It could be a tooling itself might require these kind of effects. Okay. So that's where inverse control of imaging tools, again, you can see where the AI is playing a dominant role, right? Now, just because everything sounds rosy when you talk does not mean it is all the time. You need to look at the costs involved. So if it really does not require actuation, you don't really require to go ahead and do it because the yield rates may be low. And if you are looking at medical data, you should, and you are beaming it to the cloud for processing, etc., then you need to be sure of the data privacies, right? You should not have, people exploiting the base knowledge of each human being to, control them, right? So you might have material science limitations. Some materials which you really would like to use may not be compatible with the CMOS process. If I look at biological process, you may use gold electrodes, but after some few cents in 200, 300 cents in cycles in contact with bodily fluid, it might degrade. Right, so there are issues there, and I've just given you a list of certain companies: ST, Microelectronics, Robert Bosch, etc. They have diversified in applications in different fields. The rest of them are mostly concentrating on biomedical applications. Okay, so just to wind up pretty fast, typical dimensions and substrates for a MEMS device. This is for the introductory people. It could range from 1 micron to 500 microns. If we go down, we call them nano electromechanical systems. And we still call them MEMS, even if it's still around 3 microns, 3 millimeters, sorry. So the thickness of the device basically depends on what you start using as a wafer. So the common wafers available in market is called either a silicon wafer or SOI, silicon on insulator. So it has 3 layers like a sandwich. It has a bottom layer which is thick where you can put your circuits, and it's also the base layer which holds the whole thing up. You have a central oxide layer which we call, if you are thinking of a sandwich, that's your jam basically. and the top layer is where the device is. That is where you will etch and create suspended structures. So if you want them to be fully suspended, you should remove the oxide layer in between, right? So this is one of the standard materials, starting materials which are available. And you have to be very careful about what is the dimension, smallest dimension you want to realize on this. Based on that, you will have to choose what kind of lithography and what kind of things. Now, let me give you a glimpse of the flexible substrates. I was telling you that you do get to buy in markets in Madras and all. We get to buy them. It's basically the copper laminate onto a polyimide film. So there's a glue there because if when you laminate it, the copper will peel off very easily from the polyimide if it's heated up, right? So you have a heat resistant glue in between, and that's a trade secret for each company, right? And again, you have a similar one. So you can have two copper layers, one on top, one on bottom, and that is where you realize most of the structures. If you don't need all this, you can as well go in for glass or Pyrex material, do some hot embossing to create your channels if it's a microfluidic device. Okay, so these are the starting substrates, and this is one of the structures which we had. We've used a conducting paper as the medium for testing because this was a bio application where we functionalized the conducting paper to pick up specific genes which are indicators, biomarkers for certain diseases, yearly diseases. So we have this the main circuit board here. We put the paper in the round portion which you can see here, right? And that is placed in this thing and closed with that. The leads are taken out and this channel is open, so we can put the microfluidic, whether it's blood sample or urine sample, whatever it is there, and check for a specific disease. We can also make it light enough that you can put it into ELISA and compare it with ELISA. So you can say that, okay, you have a system which is close to ELISA, right? So the issue with having a conducting paper is that very difficult to ensure uniform conductivity across a bigger size. So that's what we were focusing on. So that's just a small example. So for the fab, how do you do it? If I am taking a soy wafer, you start from the top and remove places. You call it bulk machine when you are removing structures from an existing base. Okay, so it's a subtractive technique. The other approach you are having is you take a small silicon or whatever is your base material, then you keep depositing on top of it, which is an additive technique. And you should have some sacrificial, if you want suspended structures, you might have to have a sacrificial layer in between, just like the jam we had there in the soy wafer, which should be removed so that it's suspended. So this is a standard example which I generally use for initially for teaching. Of course, it's changed now. So the blue there is your substrate. You put in your sacrificial material, then deposit, I'm trying to make a cantilever, okay, through the bottom-up approach. So deposit your silicon on top and then you etch this portion off, you have a suspended cantilever. So this is a cross-sectional view of the same, right? So if I want to do it on soy, I need not do it on soy. I can start with a silicon, just put some oxide, you oxidize it on either side, you put a photoresist, okay, and then etch off the silicon oxide. You have a region here which is exposed. Now you take off the silicon here and make the silicon oxide suspended up to certain point, right? So this is the realized cantilever where the starting material was just silicon and it was just an oxidation and then photolithography process, right? So these are general techniques which are adopted, and depending on the material, you can have a lot of applications. This is just for a summary for all of you. So triboelectric is, I hope you all remember your static charges which are built up when you rub two things together. So you can have you don't even have to rub them. You can actually have a metal or a dielectric or two dielectrics coming in contact with each other, and then you will have surface charges built up. Now, this is what is going into most of the flexible sensors as a nano energy harvester, because a small motion means the top layer will come and touch the bottom layer and there's a surface charge which is developed. The charge can be taken as for energy harvesting. But if you are putting it on your, let's say I'm putting it on my body, because I'm breathing, due to that breathing action, the membrane could go and touch the other things, in which case I'm actually doing a sensing. So lot of applications coming up. After a long break, triboelectric has come up and gaining more importance, because you can avoid having to, have a battery in place for your pacemaker, etc. If from the motion itself, you can generate enough energy, right? So ferroelectric is something which, and thermo-optic effects are all used in phase modulators. Pyroelectric is heat-induced electric charges which are generated, so you can use it for IR detection, right? So piezoelectric, I think all of you know, that's a stress-induced EMF development. So you can use it as a sensor in your microphones. You can use it for generating ultrasonics, right? When you apply inverse piezoelectric effect, you apply an electric field and therefore create a stress and make things move, membranes move, right? Now, all these on the top are mostly related to optical applications. So I'm just leaving it there just for your information, right? So these are all additional materials you'll be adding on top of a silicon layer if you're wanting different functionalities, right? And if you are having very incompatible materials, it's very difficult to easily build it on a standard CMOS process. So if I want to grow lithium niobate on silicon, I have to struggle quite a lot to make lithium niobate sit in. Lithium niobate is a good material which will give me phase change if I apply a voltage. So I can use it for different purposes. So similarly, if I want aluminum gallium arsenide in a definite combination to sit on a gallium arsenide or a SiO2 chip, I have to do all this fabrication. I have a silicon nitride deposit on top. Then I'll flip the whole thing onto SiO2. Then one by one I will remove. Then etch this aluminum gallium arsenide. Look at the struggle you are going through to get a different material of completely different lattice constant to sit on a substrate which you want. So the more you go for different materials, you actually need to be very careful on how much effort you need to put in and whether it's actually cost effective finally, right? So this is just for you to have a glimpse of the complexities involved. So if I'm looking at BTOs, that is barium titanate oxides, etc. Now the combinations are different. You are now having aluminum nitride, which is very much compatible with CMOS processes as a phase change material. It's not that good. It can have piezoelectric effect, it can have pyroelectric effect. So to improve the functionality, they are using scandium doping. So most of the ultrasound devices, right? Devices for generating ultrasound, for hearing, etc. Now they are actually going in for scandium doped aluminum nitride. If you increase the doping of scandium in aluminum nitride, these are cheap materials which are available, aluminum nitride, very compatible with CMOS, so you don't have all the struggle with having different materials, right? So if the doping concentration goes above 30, it becomes more pyroelectric, which means for pyroelectric applications, you just change the doping level. For piezoelectric applications, you keep the doping levels lesser than 30. I think Tyndall is having a good setup with standard processes for scandium doped aluminum nitride based devices, and ST Microelectronics is also using it, right? So finally you have to evolve and find out a material which is suitable for you. So what are the main processes involved? I'm going a bit fast, okay, since I'm running out of time. So you have to deposit the different layers. You may have to transfer the pattern onto your wafer, so you will do some lithography. So depending on the size, you can do standard photolithography, or you might have to go in for electron beam or something if your structures sizes are going into nanometers, right? You have to remove, that is through etching. So you can do chemical-based wet etching, or you can do dry etching, again using RI beams, or deep RI gives a good aspect ratio. So you can etch really straight structures down to 1:20 aspect ratios easily using DPRI. So the processes which you will use are dependent on the kind of structures you want to realize. Okay, so this is just capturing to you in a nutshell the main processes. And remember that most of the cost will go into packaging. You will not make a success of any device unless you plan the packaging out. You should know how it should be packaged, how I will take it for testing, and what are the points at which the inputs will come in. So there gone are the times when we used to do single systems assembly separately, okay? And we used to do multiple wafers, cut each one out, each one is packaged separately, multiple sensors are put in and the connectivities are made. Now that is all out. We actually do wafer level processing, where in the wafer itself you have to plan out all the steps, all the packaging gets done, and all you need to do at the end is just dice it. And if you are having a different input output coming, like your RF switches or RF connectors to be put on board, that has to be done separately. Fiber has to be brought in on board, you have to do that separately. But other than that, most of it gets taken care of in the standard process. So you need to plan it out properly. So when you have an idea, this is my last slide. When you have an idea or a problem, you will actually, let's say I take this example where I wanted to create this kind of a break in the structure. To create that, I knew I had to do an interference and have multiple beam interference. So I worked out, okay, if I'm using mirrors, what kind of angles through which should I turn to create this pattern? So I do a simulation first to find out what should be the pattern here, and therefore what should be the angle in which the light should come in. Then I work back and see how much the angle through which the mirrors should turn, right? And then I look, now I have the design specifications to create the structure. Then you look at how to do that. Do I need a 3D motion? What is available? Which foundry will I give it to if I don't have a fab access in my place, right? So you will start about what is available, 2D or 3D. Okay, if you want to do 3D, then how will I go about doing it, right? So starting from the initial design, you will start with the dimensions, power requirements, how much area it will take. So that will require you to, so that's how we started doing this, right? Then since we had used copper, I knew we cannot put copper inside a CMOS thing. You have to do outside, which means the copper is deposited through some other process. So the process steps gets defined as and when we decide on the material stack you are using, right? So you can do a simulation, multiphysics simulation for optimizing all this. So again, here are now, if you had a trained system, your AI will come in here to help you, right? You have CAD tools for visualizing. So once you create, at the end of it, we'll be creating some masks for the each process step which you want to execute. So you can actually apply those masks and see through the CAD tool how the device will look like. Are we making any errors, right? And if there are, then there's a feedback going through to actually correct it. You might think it will come, maybe you missed out something while you planned it out, then that's your error. If it goes for production, it is not their error. So you have to ensure that you follow all the DRC rules of the foundry, right? And you have to finally give your mass as your output. So this is a design cycle which Siemens has. So you start with the layout, you go through the fabrication steps, look at the virtual type 3D model, then do a simulation using that on, if you actuate, if you apply voltage, what's so it's a basic multiphysics modeling, FEM modeling for this. And what do the analysis give you? It tells you what the actuation was, what's the hysteresis, what's the fatigue, etc. And if this does not work out right, you have to go back and change. And finally, only then you will send your mask out for fab, right? So you want a success, right? You don't want a failure. You also should know, where will you put my input probe in, where will I put my output probe in to actually test the device. So that is an overall view of what I thought I should convey. And I hope you benefited from it. I don't know. I went a bit fast because I had to do the base also. And I thank all my research scholars because I've used some of their results throughout. I thank NYCU Taiwan for the optogenetics part. Okay. And I didn't show you anything related to SNU Noida because combined we were doing some biofluorescence setup. So it's actually a micro resonator in which, because fluorescence imaging, the issue is that the fluorescence goes out in all directions and you need to collect everything, right? So if you put it inside a waveguide, the fluorescence gets trapped. You have to ensure that the waveguide sustains that fluorescence. Then there's no way the light can escape, which means at one point or other, you will definitely be able to capture it, right? So we are working on those kind of things. And I thank you all for your patient listening. Can I stop sharing now, or do you want me to keep it on?
Any questions from any of you?
I know I went through a lot of stuff.
Yeah, many
Yeah,
things were dealt,
yeah.
but actually you have shown us how I mean details about the MEM sensors and also how to integrate it with AI also,
Yeah,
because
so I've left some papers there. So if you go to that basic review paper, you will get more on each type. Okay.
yeah, that's what. So
Yeah.
the students, if they are interested to work on this, they can integrate these MEM sensors and AI, and they can come up with really good
Yeah.
applications
See,
also.
the recent CO2, NO2, and all that is nothing new. There are enough sensors around to do it. But if you really want a good system, we spend around 6 lakhs for one system which continuously monitors all the gases and radiation levels. Now, the idea is, can we actually replace that 6 lakhs with something more affordable for us? It also has an AI content there because it's actually capturing everything, correcting for temperature fluctuations, etc. Okay. So that was the intention with which we started doing. So uh, there are a lot of scopes, especially now with India stressing on us being independent of imports, right?
Yes, yes.
Yeah.
Yeah, surely with your talk and experience that you have shared today, many researchers, students, and other members will be benefited. And in case of any doubts also, you will be getting lots of queries, I guess, ma'am, onto your
Yeah.
email ID
Yeah,
also.
yeah, sure, sure. I don't mind. I'm also serving as a mentor for the sensor chip fabrication. So
Yes, yes.
there
That's
were detailed analysis for each of the kinds of actuation. I've skipped all that, thinking that it'd be way beyond the scope, right?
Yes, yes. Thank you,
Yeah,
ma'am. Thank you.
yeah,
Thank you for taking out your time and giving such a wonderful talk and sharing your research and work with all the students and the members. Thank you once again on behalf of IEEE Census Council and IEEE Census Council Vardhaman Student Branch Chapter. We thank you for taking out time and sharing your research, and probably in future we'll reach out to you for another topic on related to MEMS, so that students can move forward and understand what advancements are going on in this particular area. Thank you, Preeta ma'am, and thank you all the students who have joined. This webinar is live telecasted on YouTube, and it will be in under IEEE Census Council YouTube channel. So anytime the researchers can go there and listen to the talk, and it will be surely beneficial to everybody. Thank
yeah.
you. Thank you, ma'am.
Thank
Thank
you.
you,
Thank you so
everybody.
much. Yeah,
Thank you.
yeah.
Sangeeta, I am ending